Hello everyone. So today I'm going to be showing you how we can use the free-form image analysis tools built into Phoretix Toolbox to analyze some phosphor or autoradiography images. Hello everyone. So today I'm going to be running through one of the potential use cases of the Phoretix Toolbox image analysis software as compared to our other image analysis software options. So I'm looking at a phosphor image here. So you may know it as phosphor imaging, or you may have heard of it as autoradiography, where essentially a radio-labeled ligand or a radio-labeled ligand binds to a sample and produces an image in a very kind of short description way. Now, phosphor imaging or autoradiography can be used to image things like bands on a gel. So it can be used for DNA and RNA analysis and Western blotting and things like that. Largely that's been replaced by chemiluminescence, but it is still out there. People do still use autoradiography or phosphor imaging for 1D analysis. If you are using phosphor imaging autoradiography for that kind of analysis, I would say that the Phoretix 1D software that we offer is much more suited for that. It's much more workflow guided and will get you to your results quicker than trying to perform the same analysis within the toolbox. The benefit of the toolbox is exactly the opposite of things like Phoretix 1D in that it doesn't force you into a particular workflow and you're left to have a lot of freedom about your analysis. So I've got some slices of kidney here that I took from a paper on the internet, and I'll link the paper in the description below as it offers a really good insight into quantitative imaging using radio ligands and phosphor imaging. And you can see here that I've got my 4 slices. Now, slice A here has been exposed to my radioligand and then has been imaged here. The sample has then been exposed to kind of X-ray film, not X-ray film, sorry, a phosphor screen. And then slice B has only been treated with my radioisotope, not my radioligand. So the idea here is that B represents the non-specific binding of my sample. So how much radiation, what will my image look like if I had just treated it with my radioactive isotope rather than my radioligand? What would be the background, essentially? The signal that I would get if there had been absolutely no binding of my ligand to my receptor, that is represented by B. So what I want to be able to do is actually take the values from B away from all of my other images as a background measurement to get the true value of the different intensity levels of my staining, and as an extension of that, which of my samples have I seen greater binding in? Do I have a greater receptor number for my particular ligand? And if I add an antagonist to my sample, what kind of intensity of antagonism can I get for the receptor for my radioligand? All these kind of questions we can answer by performing image analysis within Phoretix Toolbox. So the first step here is if I wanted to annotate my image. Now, obviously, because this image is taken from a paper, it's already been annotated. But say I wanted to annotate different sections of my image, I can do that very easily within this mode. As you can see, simply left click and drag, and wherever you left click, an annotation will be created. I can change the text color, the background color, all those different kind of parameters for my annotations. If you have a particular style that you want to maintain, you can do that within the software. So I've got my medulla here and my cortex on the outside, and that's really all there is to label within this image, unless I wanted to also label kind of just have a little short non-specific binding label to represent that this is my non-specific binding sample. So once I've done my annotation, so phosphor imaging and autoradiography imaging is very useful in kind of brain sections, tissue slices, tissue sections, or live animal imaging and in vivo imaging. And especially with animal imaging, annotations are really useful for defining exactly what it is someone's looking at within the image. So next I'll come through to the Analyze section. So this is where we're going to start taking measurements from the image and defining areas of background, etc, etc. Now, as I explained earlier, because I took this image from simply a paper, the image quality is not great. I don't have access to the original TIFF image if it exists. I'm relying on a screenshot. So the picture quality is not great. If I come back to the image tab, I can see it's an 8-bit image, so it's not great. And if I zoom in, I'm sure it'll become very pixelated. Yeah. And this image is great just as an example because I've only really got 2 sections I need to consider. So if I come along and just grab the polygon tool, the polygon tool is what we want to use when we're dealing with sections of images that are non-uniform. So this obviously doesn't fit into the remit of a square or an ellipsis. It's a non-uniform shape, so I'm just going to left click and trace around the edge of the shape to define where I want to take my measurements from. And it's not perfect, it's hard to work out where the kind of edge of the shape is. But yeah, so I'm going to call that my medulla. I'm aware that it's a bit rough. However, I'm also aware that it's very boring watching someone try and draw a shape. So I've got my sample there. I can give this a name. So let's say I'll call this sample A medulla, and you'll see that that's now it's got a label there beneath that shape. And in my sample table, I've got the name written there, so I can keep track of this shape, and I can use it for comparisons and things like that. And then for the rest of the shape, I can add in a secondary tool. I can add in a secondary polygon shape, which is going to be my cortex. And I'm aware that this is not the most accurate way of doing it, but again, I don't want to bore you. So I will just come around the outside of the shape, and I'll just trace around my medulla to make sure that I'm only taking into account my cortex. Now, what I could do is measure the shape as a whole as well as part of the cortex and do some subtraction of volumes and things like that. But I think it's just going to be easier to separate them off here like this. So I'll complete this shape. So there's my cortex shape, as you can see. So now I've got the 2 sections. I can take the background of this shape and take it away from the volumes, the levels, the areas that I've got for this shape. So if I come through with my polygon tool again, so I can roughly see where the medulla is here. Now, if these were the same section stained multiple different times, I would simply be able to copy and paste the shapes because the shapes should be the same. However, because these are all, and you can see this if I zoom out, no, it's the same. It's the same slice. Okay, in that case, what I can do is I can take my first shape and I can copy and paste it and drag it into position over my non-specific binding sample. So I know that this shape here and this shape here are the same. So realistically, if I take the background from the average background from this shape and compare it to that shape, that should perform my subtraction for me. And as these shapes are the same, I can do exactly the same with the cortex. So if I come through to sample A and I've got my medulla, and I can define what I want the background to be. So what I want the background to be So we've got three different methods for comparing shapes and for using shapes as a background measurement. We can use the shape minimum, the shape maximum, or the shape mean. And what that means is we can use the minimum value within a shape, we can use the maximum intensity value within a shape, or we can use the mean value within the shape. I'm going to go with mean. So just average all of the intensities of all of the pixels within the shape, take it away from all of these pixels. And I'm going to choose my background shape, which is number 5. And it's telling me here, that's my background level, that's my background as a volume measurement. So volume minus background, this is the mean, and that's the standard deviation there. So you can now see that we've got a volume and an adjusted volume. So basically the volume minus the background. So we've now got the intensity value for our medulla minus our background. And again, we can do the same for the cortex. Again, we can get a background adjusted volume measurement. So because these are all the same sample, we're expecting all of the same areas within the shapes and things. If you did want to measure different shapes in different areas, if you had different tissue samples, you could do that again using the same tools and the same kind of calculations, etc. So if I again take the same shape, so if I take the same shape and drag it onto my other sections, I can compare across my different experiments. Now, obviously, I want all of these shapes to also have the same background, to also target the non-specific binding background. So I want to set those to shape 5 as well. So you can see that they've all got the same background level. And their adjusted volume, you can see that this has the lowest adjusted volume, and you can visually see this as well. This is the fainter staining. This lies somewhere in the middle of this sample A and sample C, and that's reflected in the volume, in the intensity of the staining within this image. And then again, I could do the same with the cortex as well, to use the non-specific binding image as a background subtraction method for my other images. So I'm aware that's a pretty quick and dirty analysis that I performed there, but I just wanted to show you how we can use phosphor images, autoradiography images, kind of live animal tissue images in the Phoretix Toolbox, and how we can perform that analysis, and how we can use the different background removal functions and the different editing and drawing tools within the software to perform that analysis. But again, as ever, thanks for watching. And if you'd like to try out Phoretix Toolbox to perform some phosphor image analysis of your own using your own images from your own lab, please check out the links in the description below for a free trial.